Hello students, so in this session we are going to see about the growth of current in an inductor. We have discussed while discussing the introduction of self-inductance, when a coil is there, it will create a slight delay in the circuit for the current to become steady. I shall say that once again. Suppose if this is a battery and there are few many turns, and if this is resistance, okay, EMF, this is an inductor. So generally, if there is such an inductor, what is the current through this? Generally, after some time, maybe after few seconds, if we see, this inductor will behave like a short circuit. This inductor will behave like a short circuit in this network. Why? Because once the current is steady, suppose if there is a switch here, we are switching on. So at a time t is equal to 0, there was no current in this. When we switch on, when current comes, it is just like a new experience for the inductor. This is like a current is increasing from 0 to some value. Definitely this will oppose. Because of this opposition, already we have discussed this, there will be a slight delay. This much time delay will be there in order for the current to become E by R. So if this is at a time t is equal to 0, after some time, after few seconds, the current in the circuit will become E by R. So that time this inductor will act like a short circuit, just like a resistanceless wire. So this is immediately after switching on, inductor will be opposing, so there will be a delay. After some time, when the current becomes steady, then it is no more a new experience for inductor. Current is steady, current is constant. So that time what will happen? This inductor will not create any opposition, simply it will become a short circuit and current will become steady. All these things will happen when the source is DC. When the source is DC. If the source is AC, alternating current, the current behavior will be what? Current will not be constant. It keeps on increasing or decreasing. So their inductor behavior will be different, that we study in the chapter alternating current. So here this is what? So we can say that, okay, at time t is equal to 0, current will be 0 in the inductor. That is, inductor acts like an open circuit. That is, at this point, inductor will not allow any current to pass. So that point we can say current will be 0. Inductor will behave like an open circuit, just like this. This is its behavior now. Clear or what? Okay. Then second point is, after some time, inductor acts like a short circuit. This is open circuit, short circuit, and current is equal to what? E by R. So that time it will behave like this. So this circuit is for this statement. Okay, please note it down, all these points. Pause the screen and note it down. Clear? Okay, so immediately after switching on, current will be 0. After some time, current will be E by R. So between this, what is the behavior? So we need a complete expression. Okay, so whatever be the time instant, we should be in a position to understand the current. Maybe just after few microseconds after switching on, we don't have any idea with this data, so that we will see. Clear? Say a battery, a switch, inductor, okay, resistor, inductor, okay, this one. So at a time t is equal to 0, we switched on. We switched on at a time t is equal to 0. So what will happen? A current will flow. Current will flow. So just like we did in current electricity, we will mark the terminals, negative, positive. Current is flowing in this direction, positive, negative. What about this one? Here for this inductor, at a time t is equal to 0, I was 0 here. So when current is switched on, when it is on, it is like current is increasing. So current is increasing means this inductor opposes. How it will oppose? Just like developing an induced EMF in the opposite polarity, opposite direction. This thing we have seen in the previous video. Okay, now what will be that that voltage across inductor will be what? Minus L di by dt, minus L di by dt. Now this polarity is this negative and this polarity will be matching, correct or what? When we move in this direction, current. So phi is equal to what? Li. EMF is equal to what? Minus d phi by dt. That means the current due to current in the inductor, or this is equal to what? Or we can say V or E, anything in the inductor, minus d phi by dt. This is equal to minus d by dt of Li, d by dt of Li. Since this self-inductance is a constant, minus L into di by dt. This is how we are writing this. Now applying KVL, minus plus, so E, plus minus minus IR, then plus minus minus L di by dt is equal to 0. This is same as what? E minus IR minus VL. Just put the magnitude, otherwise we will get confused. Okay, clear? Now our task is to find the expression for current. We need to find the expression for current. We will do that. So L di by dt is equal to E minus IR. Okay, now we will bring this term here, dt we will put here. So dt is equal to what? L by E minus IR into di. Clear? Now we shall, this is for that short duration of time, so we need to find the current for all situations. So let us find. So how to find current for a time t? We will integrate this. Okay, we'll integrate this. Clear? So t is equal to integral dt. This is equal to what? Integral L by E minus IR di. Okay, so now when we integrate this, we will be getting T is equal to what? What about this? L into natural logarithm of E minus IR divide by, okay, fine, divide by minus R plus constant. How this comes? Suppose integration of 1 by a plus bx dx, if we do, this is nothing but log of a plus bx, and whatever be the coefficient of this variable, that we will have to divide. Clear? That is how we are getting this. Now we need to find what is the value of this constant. So for that, at a time t is equal to 0, what is the current value? I is equal to 0. When current time t is equal to 0, I is equal to what? 0. So substituting that here, 0 is equal to minus L by R. This current value 0, so this also will become 0, log E plus C. So we are getting C is equal to what? L by R log E. Okay, note down till this. Pause the screen and note it down. We'll continue from there. Okay, shall I erase this part? Okay. Okay. So, what is the expression? Yes, this one. T is equal to minus L by R log of E minus IR. Then we will substitute for C. Which is nothing but L by R logarithm of E. Okay, so this is what. Now we will take this R by L to this side. So this will become RT by L. We'll put negative here. Okay. Okay, we'll take this negative to this side. Okay, fine. RT by L, we'll keep it there. RT by L, correct or what? Okay, so this will become natural logarithm of E minus, okay, we will make it negative here, and so this will become E minus IR minus natural logarithm of E, correct or what? Okay, so when we put negative to this side, this is now negative and this will become positive. Clear? So minus RT by L is equal to, this is nothing but natural logarithm of E minus IR divided by E. Okay, now so if we need to remove this natural logarithm, this will become minus E raised to RT by L. This will become E minus IR by E. Okay, so E will move to this side. E into E raised to minus RT by L is equal to E minus IR. So I need to find this value of current. So I will bring this to this side, this part to this side. So E minus E into E raised to minus RT by L. So current is equal to E minus E into, that is EMF into exponential divide by R. So current is equal to E by R. If I take outside, this will become 1 minus E raised to minus RT by L. Okay, RT by L. E by R is the maximum current value. So I can put like I is equal to I naught into 1 minus E raised to minus RT by L. Okay, E raised to minus RT by L. Clear? So this is the expression for current. Current is equal to the maximum current into 1 minus E raised to minus RT by L. Clear? Please note down till this. We will analyze this equation. Clear? Okay, shall I raise remaining things? Okay, so this is the expression for current in the inductor. This is the expression for current in the inductor. Okay, so I is equal to what? I is equal to I naught into 1 minus E raised to minus RT by L, or I naught is nothing but the maximum current E by R. Now at a time t is equal to 0, at a time t is equal to 0, what is this value? I is equal to I naught into 1 minus E raised to, here this is 0, so E raised to 0 we can say. E raised to 0 is what? 1. So I is equal to, this is 1 minus 1, so this value is 0. So at a time t is equal to 0, the value of current is 0. Then at a time t is equal to infinity, means after some time, I is equal to I naught into 1 minus E raised to, here if we put infinity, this is nothing but E raised to minus infinity. So I is equal to I naught into 1 minus 1 by E raised to infinity. So E raised to infinity is infinity, this will become 1 by 0. So this will become, E raised to infinity is infinity. Okay, 1 by infinity is what? 0. So this is nothing but I naught. So at a time t is equal to infinity, the value of current will be I naught. At a time t is equal to 0, the value of current is nothing but 0. Already we know this fact. So this answer also, or this results also, we are getting from this equation. Okay, so any intermediate value, okay, any intermediate value if we give here for time t, we will be able to find the value of current also, okay, in inductor. Graphically we can draw like this time t if this is I. So how to draw this here graphically? So this is just like at a time t is equal to 0, the value of current will be 0. At a time t is equal to infinity, the value of current will be maximum. So here we are having I naught equal to E by R. Suppose if this is the value, this will increase exponentially. Okay, this will increase exponentially. Clear or what? This will increase exponentially. Clear? This is how the growth of current in the inductor. Please note it down. Clear? Shall I erase? Please pause the screen and note it down. Okay. Okay, so this is called the Helmholtz equation. Okay, Helmholtz equation, that name is there for this equation. Now there is something called inductive time constant. Inductive time constant, which is called tau L. Okay, its value is nothing but L by R. So if we substitute there, we can write I is equal to I naught into 1 minus e raised to minus t by tau L. T by tau L. So what is this inductive time constant? What is this inductive time constant? At time t is equal to tau L, that is when time becomes inductive time constant, or we can say when time is equal to what? Same as the value of L by R, we can say I is equal to I naught into 1 minus e raised to minus, here R by L is there, into time will become what? L by R. This L, R, everything can be cancelled off. So I is equal to I naught into 1 minus e raised to minus 1. E raised to minus 1. So this will become 1 by e. 1 by e. What is the value of e? Value of e is 2.318. So this will become I naught into 1 minus 1 by 2.318. Okay, so when you simplify that, I'll use here. When we simplify that, this value, if we simplify, we'll be getting I is equal to 0.632 I naught. That is, current becomes 63.2% of maximum value at tau L. So tau L is, or inductive time constant is, that time at which the current will become 63%, almost 63% of, suppose if this is 100%, somewhere like this. So here this is tau L. Here this becomes 63% of I naught. Okay, so that also we must understand. So current becomes 63%, that is enough, 63% of the maximum value. Clear? So exponential growth. Okay students, hope pause the screen and note it down, all the things. Okay, so this is about growth of current in inductor. Now there is decay of current in the inductor, that also we will see. So now we will see the decay of current in the inductor. Okay, the growth of current in the inductor, we have derived a formula I is equal to I naught into 1 minus e raised to minus RT by L. So growth of current, we should depend on this formula in order to understand what is the current. This is exclusively for what? When the current is growing. When the current is growing, we can use this formula. At a time t is equal to 0, we are getting I is equal to 0 at a time t is equal to 0, and I will be I max or I naught at a time t is equal to infinity. So all these are about the growth of current. Okay, this is what we have seen. Suppose if the current is decreasing, then the story will change. Okay, so that is what we are going to see now. So in the previous circuit, okay, so in the previous circuit, say resistance, inductor. Okay, so suppose here is a connection. If we have the battery connection here, okay, so then another connection is like a plain connection. So here the switch is there. Okay, so this can be either we can put into battery or otherwise we can connect here. Okay, so there is a switch. This is the switch. So either we can connect here, we can connect here. So in the previous case, that is when the growth of current was discussed, we connected like this. Okay, this switch I haven't shown there, but it is understandable. It was this connection. Now this time what we are going to do, we are going to this connection we are connecting here. We are connecting here at a time t is equal to 0. So already the current was going, this current due to this battery and this setup, it was already there. So the current was going. So we can say plus minus current is going, but this current is what? Decreasing current now. Correct or what? This current will become 0 now because battery is removed. So we are going to have decay of current. So obviously this will try to support this current. This will try to support this current. What should be the polarity then? This is how the connection should come. Correct. So if I write KVL, this is going to be IR, and this is going to be what? Minus IR, minus a plus minus. I am taking like this loop, I am taking like this. Which one? Here, just like this. This is how I am taking the loop. So minus IR, and here it should be plus VL is equal to 0. Now the one trick which we need to understand here is VL is what? Minus L di by dt. Minus L di by dt. Okay. Now this L is this minus is addressed here, so I am removing this because already we have put the sign. But di by dt is equal to what? I2 minus I1 divided by what? The change in time or time duration. Since the current is decreasing, we can say that I2 is greater than I1. Current is decreasing. Correct. Current is I1 is greater than I2. Okay. Current is decreasing, so I2 will be less than I1. So di by dt is going to be what? Going to be negative. So overall, when I am going to write this equation, this will come like minus IR minus, because of that di by dt, I can write L di by dt is equal to 0, or overall I can write IR plus L di by dt is equal to 0. Clear? Okay, so plus minus, actually this polarity should come like this, but when we consider the di by dt negative, previously we did not consider because di by dt will be positive because the current was growing. Okay, clear? Now we will play here. IR is equal to minus L di by dt, and dt is equal to what? Dt is equal to, just like we did in the previous case, this will become minus L by R di by I. Correct or what? Clear? Now when we integrate, t is equal to what? Okay, minus L by R integration of di by I. Okay, note it down. Pause the screen and note it down. We'll continue from there. Okay, done. Okay. Okay, so t is equal to what? Minus L by R. Integration of that is nothing but natural logarithm of I plus C. So now we need to find this constant. So at a time t is equal to 0, what is I? I is equal to I naught, that is maximum current. Initially it has reached the maximum current at a steady state, then only we changed the switch. So initially at a time t is equal to 0, we had maximum current. We are studying about decay of current here. I is equal to 0. So 0 is equal to minus L by R ln I naught, natural logarithm of I naught plus C. So we are getting constant is equal to what? This will come here, L by R logarithm of I naught. Logarithm of I naught. So finally we are getting the expression t is equal to minus L by R log I plus L by R log I naught. Log I naught. Note it down. Log I naught. So then taking minus RT by L to that side, we will be getting this is equal to logarithm of I minus logarithm of I naught. So minus RT by L is equal to what? Logarithm I by I naught. I by I naught. Now if I take exponential for this, e raised to minus RT by L is equal to, this will become I by I naught. So current value I is equal to I naught into, that's maximum current, into e raised to minus RT by L. Okay, so this is our expression for decay of current. This is our expression for decay of current. Clear? Note it down. Okay, hope this is copied. Okay, shall I erase this? Okay, so current was maximum at I naught. Okay, so e raised to minus RT by L, this will decay exponentially. This will decay exponentially. Clear? This will decay exponentially. So when the time t is equal to inductive time constant, that is L by R, we can substitute here I is equal to I naught into e raised to minus R by L into L by R. That is at a time t is equal to inductive time constant. So this is nothing but I is equal to I naught e raised to minus 1. So this is e. So I will be equal to I naught divided by 2.718. 2.718. So if you simplify this, this is nothing but 0.36 I naught, or I is nothing but 36% of I naught at time t is equal to inductive time constant tau L. Okay, note down this also. Clear? Fine. So at inductive time constant, the growth of current will become 69%. At inductive time constant, the decay of current will become 36%. Okay, inductive time constant is nothing but L by R. So with this, the self-inductance, okay, topic we have covered. We will do problems on self-inductance. Okay, hope you understood the growth of current, decay of current. For growth of current, remember the formula I is equal to I naught into 1 minus e raised to minus RT by L. For decay of current, use this formula I is equal to I naught into e raised to minus RT by L. Okay, if it is immediately switched on with the battery, okay, the current will not be allowed by the inductor. That time, immediately after switch on, the current will be zero in the conductor. It is like open circuit. After some time, okay, it will allow current. That time it will become short circuit. Okay, so we can say that graphically already we have drawn that graph, but one more thing I shall show in that. Okay, so in the growth of current, okay, this will become constant value. So till this, okay, once it becomes steady, I t, this is called a steady state, and this is called a transient state. So at a steady state, current will become maximum. transient state, it will be phasing that change. It will be phasing that change. Inductor will behave in a different way. Okay, so at this point it will allow maximum current. Here it is going to be short circuit. It will behave like a short circuit, just like a wire in the circuit. At this point, immediately this will be open circuit. The inductor will behave like a open circuit. Clear? Okay, so okay students, so this session is growth and decay of current. We will see some problems also. Okay, fine, thank you.
Hi students. So in this session we will try to do some problems on the topic self-inductance. So in self-inductance, what are the formulae which we need to keep the mind on? First one is phi is equal to the flux induced is equal to what? Li. Phi is directly proportional to I. So its proportionality constant is what is self-inductance. So phi is equal to Li. Another thing is EMF. Induced EMF in an inductor is equal to minus L di by dt. Third thing which we need to understand is the current value if it is growing in the inductor, which is nothing but the maximum current into 1 minus e raised to minus RT by L. And fourth one is regarding decay of current, the maximum current into e raised to minus RT by L. That's it. Okay, now we will try to do some problems. So the first problem is what is the self-inductance of a coil in which the magnetic flux of 40 milliweber is produced when a 2 ampere current flows through it. So this is a direct question, simple question. Magnetic flux is equal to Li. We need to find the self-inductance of the coil. So L is equal to phi by I. Phi is given as what? 40 milliweber, and the current is given as 2 ampere. So this is going to be what? Current is actually 2 ampere. So milliweber per ampere, we can say that this is going to be how much? 20 millihenry. 20 millihenry. That is the answer for this question. Moving to the next problem. Okay, a coil has inductance of 4 millihenry. L is given. If the current through the coil changes from 0.25 ampere to 2 ampere during 0.5 seconds, which is nothing but di by dt, or delta I by delta t is what is given. Find the average voltage dropped across the inductor. So E average or VL average is equal to AL. Instead of saying delta I by di by dt, let us write like a delta I by delta t. So 4 millihenry is given as the self-inductance, and current changes from 0.25 to 2 ampere. So 2 minus 0.25. 2 minus, okay, 2 minus 0.25 divide by how much time it takes for that? 0.5 seconds. So this is actually L into what? I2 minus I1 divided by the time duration. Okay, so when we do this, we'll be getting 4 into 10 raised to minus 3 into, this is actually 1.75 divided by 0.5. So when you simplify this, okay, minus can be kept here, minus, or if it is only we need to know the magnitude, we can avoid the minus also. So based on the options in the multiple choice questions, we can do. So this is actually 14 millivolt. Okay, the EMF induced is actually minus 14 millivolt, or 14 millivolt direction can be found if it is really necessary. Okay, we will move to the next problem. Next problem is a coil has a self-inductance of 10 millihenry. What is the maximum magnitude of induced EMF in the inductor when a current I is equal to zero point 0.1 sine 200t ampere is sent through it. So E is equal to what? L. Magnitude of E is equal to what? Sine is not there in the option. Directly we will go with the magnitude. L into di by dt. Di by dt. Current is given. So let us find di by dt. This is nothing but d by dt of 0.1 sine 200t. So when you differentiate this, we will be getting 0.1 into cos 200t, and that inner term that we need to differentiate again according to chain rule. Okay, a function inside another function into 200. So we will be getting this as 20 cos 200t. This is what is di by dt. Di by dt. Now what we need to find? We need to find maximum EMF. So let us find what is di by dt max. Di by dt max is how much? 20. 20 will happen when this cos 200t is equal to 1. Maximum value of cos and sine is 1. So di by dt max is equal to 20. So now the maximum EMF is what? L di by dt max. L is constant. So we are searching for the maximum value of di by dt. So the inductance value is given 10 millihenry. So 10 into 10 raised to minus 3 into 20. So we are getting 200 into 10 raised to minus 3, which is nothing but 0.2 volts. 0.2 volts. So looking at the options, 0.2 volts is there, option D. Okay. Okay, clear or what? E is equal to L di by dt. L is constant. Maximum EMF we need to find. So we took di by dt. Its maximum value we found, substituted in the E max formula, and got the answer. Is it clear? Moving to the next problem. Okay. Next problem is the current in a solenoid of 200 turns having length of 20 centimeter and a radius of 1 by 2 pi centimeter changes at the rate of zero point 0.2 ampere per second. Find the EMF induced in it. So again, E is equal to what? E is equal to L di by dt. So magnitude of EMF is equal to L into magnitude of di by dt. What is the value of L in the solenoid? The value of L in the solenoid is what? Mu 0 n square A L. Inductance is equal to mu naught n square A into L. That L is length. Okay, this is length. This is length. This is inductance. Okay. So this here n is what? Total number of turns divided by L. So if we want, we can write in this way: mu 0 n square divided by L square into A into L, so that this L and this L can be cancelled off. Now what is L? L is equal to 4 pi into 10 raised to minus 7 mu naught value into 200 turns are there. So 200 into 200 into pi r square, area pi r square. So R is given as 1 by 2 pi centimeter. So 1 by 2 pi into 10 raised to minus 2 the whole square. Okay, area, and divide by what? Divide by its length 20 centimeters. So 20 into 10 raised to minus 2. Okay, this is what is L. Now what else we need? We need to find EMF. So di by dt is there. So first we will find this, then solve. So here when we this 2 is squared, that can be cancelled with this is 4 pi. This pi square be cancelled with the 2 pi's are there. Pi is here, then pi another place. Then this 10 raised to minus 2 square will become 10 raised to minus 4. that can be cancelled with these four zeros, and this 2 can be cancelled with this 2. Finally, we are getting 10 raised to minus 5 into 10 raised to 1. So I am getting here what? 10 raised to minus 4. 10 raised to minus 4. Let us check once again. 10 raised to minus 7 is there. Okay, here 2 is there. 2. Okay, so 2 into 10. Okay, we'll write again. Okay, so here this 2 is there. So 2 into 10 raised to minus 7. Then here one 0 is there. This is 0 and 10 raised to minus 2. If we cancel, this will become 10 raised to minus 1. So here again 10 will come. Let it be there. Now, what about EMF? EMF is equal to L di by dt. So L is 2 into 10 raised to minus 6 into di by dt is how much? 0.2 we have got. So this is actually 0.4 into 10 raised to minus 6. So let us make it 4 into 10 raised to minus 7 volt. That is there in the option. Option B is the correct answer. Clear or what? Okay, solenoid EMF we need to find. We found self-inductance multiplied with the di by dt. Clear? So 0.2 ampere per second is nothing but di by dt. Okay, that we should understand. Next problem. Okay, how many meters of a thin wire are required to manufacture a solenoid of length L0 and inductance L? How many meters of thin wire are required to manufacture a solenoid of length L0 and inductance L? Okay, so let us do here. Suppose if we consider a solenoid, L0 is actually this length. That is length of the solenoid, not the length of the wire. The inductance of the solenoid can be considered as L. Okay. Now we can say that in one turn, suppose if we consider what the radius of one turn as R. Okay, this is R. Then we can say that in one turn, the length is actually how much in one turn? 2 pi r length. In one turn, there is 2 pi r length. So total length will be what? Total length. Suppose total length if we consider as x, this is nothing but for one turn it is 2 pi r. So this is going to be 2 pi r into n, total number of turns. This is what is total length of the wire. Now, what is the inductance of a solenoid? Solenoid inductance is mu 0 n square a divided by what? L naught. Correct or what? So here we can say L is equal to mu naught n square pi r square divided by L naught. So from this we can say n is equal to what? L into L naught divided by mu naught pi r square root. Pi r square root. So let us substitute here. X is equal to what? 2 pi r into root of L into L naught divided by mu naught pi. If we take this r outside, this will get cancelled off. Now let us take it inside. We will be getting the total length is equal to what? 2 if we take out inside, that is this is going to be 4. Pi if we take inside, that is going to be pi square, but that will cancel with the denominator pi. So 4 pi L naught L divide by what? mu naught. Okay, yeah, I think that will be sufficient. 4 pi L naught into L divided by mu naught. Yeah, option D is the correct answer. Clear? So this much length is required to manufacture a solenoid of length L naught and inductance L. Okay, clear? Shall we move to the next problem? Okay, next problem is, okay, see, the key K is closed and bulb is glowing suddenly. The key is open, what will happen? Okay, means the bulb was glowing actually. When suddenly the key is opened, now what will happen? What is the option? So you can think about your answer. Okay, before looking at the solution, just have your answer itself. Okay, what will happen? Answer is bulb goes out instantly. Is that correct? This inductor will not allow that to happen, because immediately when the current becomes zero, inductor will try to maintain that current. So bulb will not goes out instantly. Option B is bulb keeps glowing with the same intensity, not possible without current. It keeps on glowing. That is not possible. C is bulb glows brightly for a moment, then goes out. That is the answer. Why? Because this inductor will maintain current for some moment of time, at least few microseconds. After that, it goes out, because after that, when the current becomes zero steadily at a steady state, inductor will not give any response. That will just normally act like a short circuit if current is there. If current is not there, then nothing will be there. So option C is the correct answer. Option D, bulb keeps glowing with the dim light. No current is available. Option C is the answer. Clear? Okay, shall we move to the next problem? Okay, next problem is, if R is equal to 2 ohm, if R is equal to 2 ohm and E is equal to 24 volt and inductance is 4 Henry, current is 10 ampere. That 10 ampere is decreasing at the rate of 0.5 ampere per second. Find the potential difference between Vn and Vm. So this is what Mn. Resistance is 2 ohm. This is 24 volt. Battery is 24 volt. And here there will be voltage drop VL. How much will be VL? VL will be L di by dt. So its value is going to be 4 into 0.5. 0.5. What will be the polarity? Here the current is decreasing, so it will try to maintain current. So the polarity will be like this. This current is, the current direction is what? This is the current direction. What is high? 10 ampere current is coming. So this 10 ampere current is decreasing, going to decrease, or it decreases at that instant. So this all things happens in instance of time. So to maintain that current, it will have polarity in this direction. That is what. Now, current electricity, we have seen circuits like this. Only thing is that inductor was not there, but instead of inductor, we will replace with that EMF or battery kind of symbol. We can replace if we want for feeling comfortable. Okay, so this is easy. So from where we will start? We will start from N. We have seen this kind of circuits. So Vn, well, while coming in this direction, 4 into 0.5, 4 into 0.5 is the 4 into 0.5 is the voltage drop at the inductor. 4 into 0.5. So what is that value? 0.5 into 4 is 2. So let us take this as 2 volt. So Vn coming in this direction, let us put the symbols also. Okay, so this is plus minus already there, plus minus. Okay, all these things we will put. Oh no, I'm sorry, plus minus for resistor we will have to put like this because current is flowing. Okay, so Vn
minus 2 minus 24, and here this is going to be plus 20 minus Vm is equal to 0. So we will be getting Vn minus Vm is equal to how much? This is 26 minus 20 is equal to 6 volt. This is the correct answer. Option C is the correct answer. Okay, so how we should put the polarity of voltage of inductor? That is important. If the current is increasing, then put the polarity in the opposite direction of current. If the current is decreasing, put the polarity in the direction of current. Then whichever potential difference we need to take, just write the equation as we have studied in current electricity. If we do not know Vn minus 2 minus 24 plus 20 minus Vm is equal to 0, if your problem is in this, then we must study current electricity. Study current electricity properly, mainly the topic of circuit theory. If you just study circuit theory, this thing is easy for us. Okay, we'll move to the next problem. Okay, so find out the self-inductance L of the coil whose resistance is 2 ohm and current is I is equal to 1.5 ampere, which is increasing at the rate of 10 raised to 3 ampere per second. So circuit is given. Okay, fine. We need to find the self-inductance. Okay, so and the current is increasing too. The current is increasing. Okay, so if the current is increasing, what must be the polarity? It should be connected in the opposite polarity, because current is coming like this and this current is increasing. This polarity will be to opposite. Okay, so this is going to be what? L di by dt in the opposite direction. So if we put KVL in this direction, we can write, okay, this is plus, this is minus. So 6 minus L di by dt. What is the value of L, which we need to find out? L, what is di by dt? At the rate of 10 raised to 3 ampere per second. So 10 raised to 3 can be put here. Minus here, what is IR? So 1.5 into 2. 1.5 into 2. This is equal to 0. So L into 10 raised to 3 is equal to what? Okay, 6 minus 3, 3. So L is equal to what? 3 millihenry is the answer. Option C. 3 millihenry is the answer. Option C. Okay, is that clear? Okay, we will move to the next problem. Okay, question number 9. Find the current in resistance R1 and R2. Question A is just after switch is closed. Question B is at a steady state. So A, when the switch is closed, when immediately after the switch is closed, okay, what will happen? Inductor will behave like an open circuit. Okay, because the current, sorry, inductor will behave like what? Immediately after switch is closed. So initially at a time t is equal to 0, there was no current in the circuit. When switch is on, what will happen? The current will develop in the circuit. That is, actually current is increasing. So that time the inductor will behave like a open circuit. Open circuit. Okay. So switch is closed. This is the battery EMF. So this is resistance R1. Now what about here? Here this is going to be an open circuit. So no current will flow through this. Inductor will not allow any current to pass through this. So R1 is equal to 30 ohm. So now this is the circuit. Now what is the current through
R1, only R1 is there in the circuit. So simple circuit we will be getting. Once if we know this concept, the circuit becomes simple. So 120 volt and this is 30 ohm. So the current through R1 is going to be E by R. So 120 divided by 30. So this is going to be what? 4 ampere. Yes, 4 ampere. This is going to be 4 ampere. Clear? So, and the current through R2 is equal to 0. So this is the first, the answers for the first question, just after switch is closed. And okay, hope you understood this. Clear? Now, second case. Second case B is steady state. Steady state means the current is settled in the circuit. There is no change in current. No change in current now. There is no di by ds. No change in current. Once if there is no change in the current, once if there is no change in the current, inductor will act like a short circuit. Inductor will act like a simple wire. It will not create any opposition. There is when there is no change in the current. So 120 volt, this R1 is equal to 30 ohm, R2 is equal to what? 60 ohm. This is what the situation is now. This is a simple resistance circuit. So to find current, first we will find what is R equivalent. So R equivalent is what? R equivalent is R1 R2 divided by R1 plus R2 because they are in parallel. So 30 into 60 divided by 30 plus 60. So 180, okay, divide by 90. So this can be cancelled. So this is going to be, okay, 20 ohm. Okay, 20 ohm or what? Okay, 20 ohm is the equivalent resistance. 20 ohm is the equivalent resistance. Correct? Okay. Now what we need to find? We need to find the current in the circuit. So I is equal to what? E by R equivalent. I is equal to E by R equivalent. E is 120 and R equivalent is 20. So we will be getting 6 ampere. 6 ampere current will be there from this battery. 6 ampere current from the battery. So now we will find the current through 30 ohm. Current through 30 ohm is how much? So the total current into opposite resistance 60 divided by 30 plus 60. Our current division rule in current electricity. I1 is equal to what? I into R2 divided by R1 plus R2. Opposite side resistance we take. I2 is what? I into R1 divided by R1 plus R2. So what about this one? Now the total current is 6 ampere. 6 into 60 divided by 90. So this can be cancelled off. So here 2, here 3, this is 2. So this is going to be 4 ampere. Obviously the current in 60 ohm is going to be the balance of 6 ampere. This is going to be 2 ampere. Okay, so this is the fundamentals from the growth of current, decay of current we have studied. So from this we can understand steady state and transient state. Is that clear, all of you? So hope you understood the problems on self inductance. Okay, so we will see in another session with the problems on mutual inductance and topic on mutual inductance. Okay, thank you very much. Goodbye.